Okay, let's dive right into this explainer. If you're stepping into the world of AI product management, you don't need a PhD in computer science, but you absolutely do need the right mental models to align deep learning with actual measurable business value. So today, we're going to strip away all the sci-fi hype and look closely at the real mathematical engine that's driving modern AI.
Picture this. You're trying to program a computer to recognize a messy, handwritten number 3 on a tiny 28 by 28 pixel grid. If this is a feature in, say, your mobile banking app, your users expect it to work instantly, right? Now, for a human brain, you glance at it and you just know what it is, whether it's loopy, sharp, or tilted. But a computer, it just sees a raw grid of numbers. Suddenly, that seemingly simple task of identifying a digit feels almost impossible if you're trying to write traditional rule-based code for it. So, how on earth do we teach a machine to see what we see so effortlessly? To figure that out, we're going to use a simple 3-part framework. First, we'll explore the engine. Then, we'll step into the factory. And finally, we'll hit the showroom.
All right, part 1, the engine. Let's peel back some of these buzzwords. So what is a neural network, really? At its core, it's just a stacked model. Information flows through layers of what we call neurons. And honestly, don't get too hung up on the whole biological brain comparison. For our purposes, a neuron is simply a container holding a number between 0 and 1. Think of it like a little light bulb. If the number is close to 0, it's dim. But if it's close to 1, it's burning bright as it finds patterns in the data. Now, here is where the sheer scale of this just gets mind-boggling. To process that simple 28 by 28 pixel image of the number 3, we start with an input layer of 784 pixel activations. That data passes through hidden layers that are desperately trying to find patterns until it finally hits an output layer of 10 neurons, which represent the digits 0 through 9. Whichever output neuron is the brightest, that's the network's final answer. But the real challenge is that the connections between all these neurons have little knobs and dials. In just this incredibly simple network, we have 13,000 adjustable parameters, what we call weights and biases. Tuning all 13,000 of those correctly requires massive, expensive compute power just to get the network to confidently light up the right digit. So how in the world do we know which way to turn those 13,000 knobs? Well, the network learns by basically scoring its own mistakes using something called a cost function. When it gets the answer wrong, the cost is super high. When it gets it right, the cost is low. To fix those mistakes, we use this brilliant algorithm called gradient descent. Imagine a mind-bending 13,000-dimensional landscape. Gradient descent systematically tweaks all those parameters by finding the steepest step downhill, rolling closer and closer to the bottom of the valley where the cost is minimized and the predictions are actually accurate. But here's where it gets wildly counterintuitive. You might logically hope that as the network learns, it's looking for neat human concepts, like the curves of a 3 or the straight vertical line of a 1. But if you actually look inside those hidden layers, it's just this jumbled, chaotic mess of pixel patterns. It makes absolutely no sense to us. The crucial point here is that the network does not learn the human idea of a digit. It just finds a really weird, uninterpretable mathematical shortcut in that 13,000-dimensional valley that happens to spit out the correct answer.
Which brings us to part 2. The factory, the PM architecture blueprint.
In the real world, you're playing on a team. As an AI PM, you don't need to be in the weeds coding the optimizers or picking the hyperparameters. That is the data scientist's domain. But you absolutely own the business problem, the core success metric, and the deployment service level agreement, or SLA. Think about it. If the model takes 5 full seconds to generate an answer, but your user expects a response in milliseconds, your product fails. It doesn't matter how clever the underlying math is.
And this is exactly why your role is so critical in matching the model architecture to the specific data type and business constraint. Look at the latency trade-offs here. Say you pick a massive transformer model for a simple tabular data problem instead of a standard feed-forward network. You just drastically inflated your training costs from $1,000 to over $100,000 and spiked your inference latency to half a second. Every single neural network automates a decision, and it's literally your job to make sure the cost of automating that decision doesn't just absolutely destroy your profit margins. So, what do you do when your data science team builds a highly accurate model, but the inference latency is just way too high for your production SLA? You leverage model compression. Techniques like quantization reduce the precision of the numbers the network is using. Pruning rips out the non-critical connections, which shrinks the compute footprint by like 50 to 70%.
And then there's knowledge distillation, which uses a massive teacher model to train a super fast, lightweight student model. These three techniques are your absolute secret weapons for hitting production SLAs. They allow your teams to optimize for speed while keeping up to 95% of the original accuracy. It's a total game changer.
All right, let's move to part 3, the showroom, monetizing the black box.
First off, we really have to talk about the risks of the tech. Remember those weird, uninterpretable pixel patterns we talked about earlier? Because neural networks basically function as a black box. Relying on them blindly can have devastating real-world impacts. A few years ago, actual teachers in Houston were fired based on low performance scores that were generated by a proprietary, unexplainable algorithm. The teachers couldn't even check if the system was flawed, and a federal judge ultimately ruled that it violated their civil rights. So, to safely deploy AI in high-stakes domains like healthcare, finance, or HR, we cannot just shrug and say, well, the computer decided. No way. We have to leverage explainable AI, or XAI. Techniques like GradCam act a lot like visual heat maps, showing us exactly which pixels influence the AI's final decision. This bridges the gap between high performance and human transparency, making sure our products are both reliable and legally defensible. Now, if you can navigate those ethical hurdles and actually deliver a high-value product, the financial upside is just massive. According to McKinsey, organizations that successfully structure the monetization of their AI solutions achieve 3 to 5 times higher ROI than competitors who struggle with pricing models. You see, neural networks are super unique because they actually get better over time as they process more data. Your pricing strategy absolutely must capture that compounding value. You might use outcome-based pricing, kind of like how Viz.ai charges for actual stroke detections. Or you could adopt pay-per-prediction models, which are used by roughly 65% of AI providers right now, though often a hybrid approach of a base fee plus usage works best. The big takeaway here? Don't undervalue the network effects of your data. As we wrap up this explainer, we've gone from the raw math of a single neuron all the way to pricing strategies in the boardroom. But I want to leave you with this final, provocative thought to chew on. We've seen that these models find bizarre mathematical shortcuts that work flawlessly, but look like pure chaos to a human eye. So if a machine can consistently give the right answer for reasons that we fundamentally cannot comprehend, what does that actually tell us about the nature of intelligence and understanding itself? Thanks for diving in with me, and I'll catch you next time.